This call is now being recorded.
Okay, last meeting we stopped at this particular theorem, theorem 1.2.11, that if P is a probability function, that means our P satisfies the Kolmogorov, no, the Kolmogorov axioms, the three axioms, then the probability of A, okay, A here is an event, which is actually a subset of S. At the same time, A is an element of our sigma algebra script P. So the probability of A is equal to the infinite summation of the probability of the intersection of A and C sub I from 1 up to infinity for any partition. Take note, we have a collection of events, which is actually a partition, C sub 1, C sub 2, and so on and so forth. So in other words, the pairwise or this collection of infinite events are mutually exclusive and at the same time exhaustive, in which the infinite union of the C sub 1, C sub 2, and so on and so forth will be equal to our sample space S. So we have a name for this letter A result. We call this as the theorem of total probability. And then for letter B, the probability of the infinite union of the A sub I, no, I from 1 up to infinity is less than or equal to the infinite summation of the probability of A sub I from 1 up to infinity. That is for any sets, no? Any sets, A sub 1, A sub 2, and so on and so forth. We have no assumption here that this collection of events, A sub 1, A sub 2, is a partition of our sample spaces. So we call this inequality as the Boole's inequality. So let me proceed now to the next subsection. We have here counting. I know that you have encountered this already in your undergrad subject STT or STAT 131. Note that the methods of counting are being used in order to construct probability assignments on finite sample spaces. But it can also be used to other questions, no? To answer other questions also, this method of counting. Let's have an example here. Lottery 1. For a number of years, the New York State Lottery operated according to the following scheme. So from the numbers 1, 2, up to 44, a person may pick any 6 of her ticket. The winning number is then decided by randomly selecting 6 numbers from the 44 numbers. So to be able to calculate the probability of winning, we first must count how many different groups of 6 numbers can be chosen from 40. From these numbers, no, 1 up to 44. Okay, another example here. In a single elimination tournament, such as the US Open tennis tournament, players advance only if they win. So in contrast to double elimination or round robin tournaments. So if we have 16 entrants, we might be interested in the number of paths a particular player can take to victory, where a path is taken to mean a sequence of opponents. So to answer such problem, we need some counting techniques. And one of these counting techniques, we call it as the fundamental theorem of calculus, and it's being stated in theorem 1.2.14. Says here that if a job consists of case-separate tasks, the ith of which can be done in n sub I ways, I from 1 up to k, then the entire job can be done in n sub 1 times n sub 2 times, and so on and so forth, times n sub k ways. So we call this theorem as the fundamental method, not the fundamental theorem of counting. So if we're going to apply this theorem in our previous example, the lottery example, there are cases to consider if we're going to apply this fundamental theorem of counting. Okay, or aspects to consider. One aspect to consider is that if we're going to count with replacement, or counting with replacement, or counting without replacement. When we say counting with replacement, this process means that if we're going to pick a number from 1 to 44, then to take the second number, we must first put back the first number that we have taken, or we replace by the same number. So we call this process is counting with replacement. Otherwise, we have counting without replacement. So that's the first aspect to consider, especially if we're going to apply the fundamental theorem of counting. And another thing to consider is whether or not the ordering of the numbers is important. So the possible methods of counting here for this particular problem can be illustrated in this 2x2 table. So in the first column, we have the counting without replacement. In the second column, we have counting with replacement. And then if we're going to consider the ordering, in the first row, we have ordered. And then on the second row, we have the unordered method. So we have 4 possible ways of counting. So the first one, we have ordered without replacement here. Ordered without replacement. Then we have also ordered with replacement in this particular cell. And then we have also unordered without replacement on this cell. And then we have the last case, we have unordered with replacement. Okay, so before we're going to determine the number of elements or the number of outcomes in our sample space, consider first this definition. We have the factorial definition. For a positive integer n, the n factorial, denoted by this symbol, it is the product of all the positive integers less than or equal to n. So in other words, our n factorial here can be expressed as the product of positive integers less than or equal to n. So first we have n, then n minus 1 times n minus 2, and so on and so forth up to 1. And then by convention, the 0 factorial is equal to 1. Okay, so let us now consider these 4 possible cases. Determining the number of elements of our sample space. Okay, we have 44 numbers, and then we're going to pick only 6 numbers from these 44 numbers. If we're going to consider the first case, we have ordered without replacement. So from the fundamental theorem of counting, if we're going to consider the first position, say since it's ordered without replacement, in the first position there are 44 possible ways that we can put 44 numbers on that first position. Okay, since counting is without replacement, so hindi na natin isasauli yung number na yun na nakuha natin. On the second place, or in the second order, there are only 43 possible numbers that we can put. And then on the third order, Okay, since this is without replacement, then we have only 42 possible numbers kasi nakuha na yung dalawa. So, 42 na lang yung naiwan. And then, so on and so forth. 41 yung in the fourth place. In the fifth place, we have 40 numbers. And then on the sixth order, then we have 39 numbers that we can choose to put on that particular space. So we have here 44 times 43 times 42 times 41 times 40 times 39. And this is equal to 44 factorial over 38 factorial. If we're going to compute this, then we have this big number. We have this large number. We can simply write this as the number of numbers n factorial over n minus r factorial. Taking r here to be the number, r is the number taken from n. Since we're going to take 6 numbers from n here, ordered and without replacement. So if n here is the total number of numbers, 44, so we have 44 factorial, and then 44 minus 6, that is equal to 38. So we have 38 factorial. So we have here the number of elements or the number of outcomes in our sample space. Itong number na to. So these are the possible number of tickets. And then another thing, or another case, if we have ordered without replacement, or rather, ordered with replacement. So kung ano yung makukuha natin na number, we're going to replace it by the same number, or we're going to return that number. Then after that, we're going to pick the next number. Okay, so here are the 6 numbers, possible spaces for the 6 numbers. So for the first space, there are 44 possible numbers that we can put from 1 up to 44. Since this is with replacement, on the second space, we can put also 44 numbers. At the same time, similarly to other spaces, we can put 44 numbers. That is why the answer is 44 to the 6. And this is the number of elements in our sample space, or the number of outcomes in our sample space, or the number of possible tickets. Excuse me for a while. Are you there?
Hello, sir.
Okay lang. I thought nawala ang internet. Yes, Kim? Sino nag-raise na hand?
Okay, sir.
Okay lang. Okay lang. Let me check first. Excuse me. Okay, so that's for the second case. When we have ordered and without replacement. And then for the third case, say we have unordered, and then without replacement. Okay, so when you say unordered without replacement, walang order yung numbers natin, and then at the same time without replacement. Okay, so the number of possible tickets when ordering must be accounted. We have this permutation. Actually, this n factorial over n minus r factorial. That is 44 factorial over 38 factorial. we have here. And then we're going to divide this by the number of arrangements, no, the number of redundant arrangements of our 6 numbers. And then using again the fundamental theorem of counting, that is actually equal to 6 factorial. So we have here 6 times 5 times 4 times 3 times 2 times 1. Okay. So for the case when we have an ordered without replacement, then the possible number of tickets we have here, no, 7,059,052. Okay, this is for the third case. And then for the last case, before determining this number of elements in our sample space, consider first this definition. So for non-negative integers n and r, where n here is greater than or equal to r, then we define this symbol. Okay, take note of this symbol. Can be read as n chose r. Or sometimes this is the number of combinations, no? N number of combinations taken r at a time, or n number of arrangements taken r at a time. N chose r. So this expression or this symbol is equal to this mathematical formula, which is equal to n factorial over the product r factorial and n minus r factorial. So we call this as the combination, no? Or arrangement. It is actually an arrangement without regard to order. That is why in case 4, so we have here an arrangement, an ordered with replacement. So for this fourth case, it says here, it is the most difficult case to count. You might first guess that the answer for this would be 44 factorial, or rather 44 raised to 6 divided by 6 factorial. But this answer is not correct. So the total arrangements for this, or the number of elements in our sample space, would be equal to this number. Okay, 13,983,816. So we have 49 factorial over 6, no, the product of 6 factorial and 43 factorial. So to be able to get this answer, say we're going to consider these 44 numbers as beans. Para siyang boxes, no? Beans. Say for example, this is 1. First number 1, number 2, number 3, and so on and so forth. So we have here 43, and then we have here 44. Okay? Since this is with replacement, no, unordered with replacement, so we can choose that number by placing a marker on that particular bin or box. Say we're going to put some divisions first on our 44 numbers. These are the divisions. Okay? So ito yung divisions natin. Ibig sabihin, ito yung bin. Bin ng number 3. Ito yung bin ng number 2. Ito naman yung bin, parang box, no? Parang paglagyan for number 1. And then here, this is for number 43. And then this is for number 44. So how many divisions or how many walls that we have created from these 44 numbers? How many walls do we have here? Ilan lahat? So meron tayong 44 numbers. How many walls? There are 43.
43.
Yeah, 43 walls. Ito. Parang 43 walls. Meron tayong 43 walls. So, para sabihin natin na parang box ito or bin, lagyan natin dito ng arbitrary vertical line para sabihin natin na bin yan siya. No? Parang box na pwede natin ilagay yung ating marker. Kung napili natin yan, number na yan. So, hindi kasali itong vertical line na to at saka itong vertical line na to. So, there are 43 walls that divide these 44 numbers. Say, with replacement man tayo. Say, yung marker, yung 6 markers, we're going to put it on our bin. Say, for example, napili natin lahat, number 3. So, lahat dito, nalagay natin yung 6 markers. M. Sabihin natin, tatlong 3. Marker. M. And then, dito isa. Ito isa. So, number 1, merong isa. So, meaning to say, we have these numbers in our lottery numbers 1. We have 3, 3, 3. We have 43, and then we have 44. Okay? So, if we're going to count all the walls at the same time, all the markers there, we have 6 markers, and then we have 43 walls. So, all in all, a total of 49. Sabihin natin, parang 49. That is why we can choose 49 objects. The walls and the markers, we have 49 objects. And then since we are taking 6 numbers from these 44 numbers, then we have here 49. Okay, that's the total number of objects. And then we have here 6 for the 6 markers, and then 43 for the number of walls. So for this case, the total number of possible tickets would be 13,983,816. So we can summarize this 4 possible cases in this table 1.2.1 for the 4 cases here. If we have ordered without replacement, then we have here, we have this formula. This formula is actually for the permutation. If we have an ordered without replacement, then we have this formula, a combination of n things taken r at a time. And then if we have this case ordered with replacement, so we have n to the r. And then for the last case, if we have an ordered without replacement, then this is our combination. A combination of n plus r minus 1 taken r at a time. So this formula will give us number that would give us the total number of our sample space or the outcomes in our experiment. Hence, we can now compute for the probability of winning in a lottery. Okay, so that's all for review in the counting techniques. Any questions or any clarifications?
No, sir.
Okay, thank you for that, Kim. So let me proceed now to the next section. We have here conditional probability and independence. Okay, since we have this title for this section, conditional probability and independence, this would imply that the probability that we have learned in the previous sections, we call it as the unconditional probability. Remember that that probability is based on our sample space S. So if we have this conditional probability, that means from the given sample space S, we're going to compute another probability based now on the updated sample space. Say for example, we have here 4 cards are dealt from the top of a well-shuffled deck. What is the probability that there are 4 aces? So for this particular problem, we can solve this problem in 2 ways. So the first one, we can get the probability using the unconditional probability. And then we can also solve this problem using the conditional probability. Okay, so for the first solution, using the unconditional probability, since there are 52 cards and we're going to select 4 cards from these 52 cards, then the number of our sample, the number of elements in our sample space would be this: a combination of 52 cards taken 4 at a time. So the number of elements in our sample space here is equal to 270,725. And then if we take A here as the event of having 4 aces, okay, having 4 aces, A is the event of having 4 aces. In other words, yung event A natin, we have the ace of heart, we have the ace of club, we have the ace of spade, and then we have the ace of diamond. So we have only 1 element for that event A. Therefore, the probability of getting these 4 aces would be equal to 1 over 270,725. Okay, so pwede naman natin sabihin dyan na we have here A is the event of getting 4 aces. So in this case, the probability of A, as we have defined, the probability of A here would be equal to 1 over, okay, the number of elements in our sample space S, that is a combination of 52 cards taken 4 at a time. So this is equal to 1 over 270,725. Okay, so we solve this problem using the first definition of probability that we have, which is actually the unconditional probability. Another way of solving this problem is that we're going to apply this conditional probability. Okay, so we have here, we update. Given that we have 52 cards, 52 cards in our given we have 52 cards in our, and then we're going to pick the first ace card. So there are 4 possible ace out of 52 cards. So we have here 4 over 52. And then after that, since we already taken the first ace, then the probability of getting another ace out of the 51 cards, we have 3 out of 51. That's a probability. And then we have here for the third card, 2 over 50, and then for the last card, 1 over 49. Say we're going to have these events here, A sub I to be the events of selecting 4 cards in a sequence, or say in sequence. Such that the ith card is an ace. So I here 1, 2, 3, 4. So that means we have here the probability, itong part na to. We can express this as the probability of A1 intersection A2 intersection A3 intersection A4. And this would be equal to the probability of getting the first event, A sub 1, okay? Yeah. So we are selecting 4 cards in sequence such that the ith card, the first card is an ace. So that's actually 4/32. And then we update now our new sample space from 52 cards. The updated sample space now is 51. So the probability of A sub 2 given A sub 1, which is then the probability of A sub 3 given A sub 1 and then A sub 2. And then lastly, the probability of the event A sub 4 given A sub 1, A sub 2, A sub 3. By the way, yung expression na A intersection B, this is the same as AB. So, pwede lang probability of A1, A2, A3, A4. Okay? Parang ganito. Intersection ito, part na yan. Intersection of A1 intersection A2 intersection A3. So, the second method, we applied actually here the conditional probability. We update our sample space. Then after that, we compute the probability, and we call that probability as the conditional probability. So we have here now the formal definition. If A and B are events in our sample space S, and then the probability of B is positive, then the conditional probability of A given B, okay, this is our notation now, it is equal to this fractional expression in which the numerator is the probability of the intersection of A and B over the probability of B. Or we can write this in this manner, that the probability of the intersection of A and B will be equal to the product of the probability of B and the conditional probability of A given B. Okay, since we know that the commutative property of intersection, we can also express for here the probability of A intersection B. This is the same as the probability of B intersection A. And then this one, the probability of B intersection A is actually the probability of B, conditional probability of B given A times the probability of A. Hence, we have this form now, that the probability of A intersection B will be equal to the conditional probability of B given A times the probability of A. Okay, since equation 1.3.3 as well as 1.3.4 have the same left-hand side expression, then we can equate now the expression, the right-hand side expressions of these two equations. So as we have here in equation 1.3.5, that the conditional probability of A given B will be equal to this product. Okay, is that clear? Pareho lang naman yan. Ito, this one is equal to this. And it would imply that the conditional probability of A given B will be equal to the expression on the right-hand side in equation 1.3.5. Okay, so we call this as the Bayes rule, the Bayes rule. But in general, let us consider theorem 1.3.5. So let A sub 1, A sub 2, and so on and so forth. So we have a collection of infinite events here be partitioned in our sample space. So this collection is mutually exclusive, at the same time exhaustive. And we let B be any set. Then for each I, now for each I, 1, 2, and so on and so forth, the conditional probability of A sub I given B will be equal to this expression, fractional expression. Notice that the denominator of our fractional expression is actually the what we call the theorem of total probability. That is actually the probability of the event B. Itong part na to. This is equal to the probability of B. Just like in my argument last meeting, say we have here our sample space S, and then we have a partition of our sample space S. Say this is our event A sub 1, and then this is our event A sub 2. This one, the event A sub 3, and then A sub 4, and then that. And then if we're going to consider another event in our sample space S, sabihin natin itong B. Okay. Sabihin natin itong B. Okay, that is our B. If we're going to determine the probability, this is B. Yan yung B. So if we're going to determine the probability of B, B obviously is actually, yung B natin is actually the union, the infinite union of the intersection. Notice natin yan, the infinite union of the intersection of the A sub I and then B. I from 1 up to infinity. Sabihin natin, A sub 1 intersection B. A sub 1 intersection B, say we have here, ito. A sub 1 intersection B. A sub 2 intersection B, we have here. Ito. A sub 3 intersection B. Ito, part na yan. A sub 4 intersection B. Ito. And then so on and so forth. So we can now compute for the theorem of total probability that the probability of B, okay, since these are mutually disjoint, the intersection of that is empty set, then it will be equal to the infinite summation of the probability of A sub I intersection B. I from 1 up to infinity, or B intersection A sub I. And this would be equal to the infinite summation of yung probability of B intersection A sub I, that would be the same as the probability, the conditional probability of B given A sub J naman yung ginamit pala. A sub J na lang. A sub J. So J, A sub J, and then the probability of A sub J. Okay, so we have that in our denominator. It's according to our theorem of a total probability. And then since our concern is to be able to determine the conditional probability of A sub I given B. Say for example, itong part na to, ito yung concern natin. Itong concern natin, itong brown. Ito yung concern natin, itong part na to. So we're going to compute the conditional probability of A sub 4 given B. Okay? Yung kanina, yung concern natin is to determine the probability of B. And this time, since our concern is to determine the probability, the conditional probability of A sub I given B, so we have this formula now. Itong numerator natin dito is actually the same as this. So, meron lang yung subscript yung I natin, and then yung probability of B is actually based on the theorem of total probabilities. Okay, understood?
So,
Yes.
Okay.
Yes, sir.
yes, sir.
There are some cases that B has no effect on the probability of another event, say A, or we can write it in a symbol that the conditional probability of A given B, since B has no effect on the event A, then we have here that the conditional probability of A given B will just be equal to A. So if we have this, this would also imply that the conditional probability of B given A will be equal to the probability of B. And that is using the Bayes rule. Okay? So that means that if B has no effect on A, it would also imply that A has no effect on our event B. So in this case, if B has no effect on A, then this conditional probability, or A has no effect on B, then this conditional probability of B given A will just be equal to the probability of B. So the probability of the intersection of A and B equal to the product of the probability of A and the probability of B. This is actually what we call the definition of statistical independence. So two events, A and B, are statistically independent if the probability of the intersection of A and B will be equal to the product of the two probabilities, the probability of A and the probability of B. By the way, we can also define our probability. We can also define statistical independence in terms of the conditional probability. Say the conditional probability of A given B, if it is equal to the probability of A, then A and B are independent. Or we may say the conditional probability of B given A, if it is equal to the probability of B, then we say that A and B are independent. And take note, we can use this as long as the probability of A or the probability of B are both positive. Okay, let's have this theorem now. Okay, theorem 1.3.9, if A and B are independent events, then the following pairs are also independent. Okay, so A and B complement are also independent. A complement and B are also independent. A complement and B complement are also independent. So let us try to prove the first letter A. So if we're going to show that A and B complement are independent, that means we're going to show that the probability of the intersection of A and B complement should be equal to the product of the probability of A and the probability of B complement. That's according to our definition above. Tama ba? Based on our definition above. So to prove this, using the direct method, we start with the left-hand side of our equation. Say, we start from here. Say the probability of A intersection B complement. And according to our property that we have proved last meeting, it says that the probability, yung probability of A is actually equal to the probability of A intersection B plus the probability of A intersection B complement. So that would imply now that the probability of A, or rather the probability of the intersection of A and B complement would be equal to the probability of A minus the probability of the intersection of A and B. Okay, so we apply here the property, the property of probability function. And then on the next step, the next equality sign, we apply the assumption in our theorem. Ano yung assumption sa theorem? That A and B are independent events. So if A and B are independent events, that means the probability of the intersection of A and B will be equal to the product of the probability of A and the probability of B. And then by factoring, we can factor out the probability of A. Since the probability of A is non-negative or for any event here, and then so we have now one, the other factor would be 1 minus the probability of B. And using again the property of our probability function, 1 minus the probability of B here is equal to the probability of B complement. Since we have shown that the probability of A intersection B complement is equal to the product of the probability of A and the probability of B complement, then we can conclude that A and B complement are independent. Okay? So, try na natin yung B. We're going to prove that A complement and B are independent. So, we're going to apply the same approach. Sabihin natin, yung probability of intersection B. So dito naman, so yung probability of B could be equal to the probability of B intersection A plus the probability of B intersection A complement. So this would equal to probability of B minus the probability, okay, of B intersection A. So with the probability of B, and then since B and A are independent, so we have the product of two probabilities. We can factor out the probability of B. Then so you have 1 minus the probability of A. And we have now the probability of B. And then 1 minus the probability of A equal to the probability of A complements. Okay, therefore, A complement and B are independent. Can you try? Anybody can try? Letter C. How to prove letter C? Show that A complement and B complement are independent. Madali lang yan, no? So, I'm going to leave that to you. Try to prove that result, that the A complement and B complement are independent. Okay, so that's for the section conditional probability. We have defined our conditional probability and at the same time independence. Any questions or clarifications for that section?
So far, sir.
None so far? Okay, thank you, LJ.
Done so far.
Para review lang naman yan. Let's proceed now to the next section. We have what we call random variables. Okay, so I have here, before defining a random variable, say for example, we're going to consider an experiment of tossing a coin 25 times. Okay, we toss a coin 25 times. So how many outcomes do we have for our experiment? Now, this is our experiment. We toss a coin 25 times. How many elements or outcomes do we have for our experiment? Anybody? Counting technique lang naman. Hello?
Dito ang tails, sir.
LJ?
Sir, kasali dito ang tails. Pag mag-toss ng 5 times.
Yeah. Isang coin lang naman. You toss a coin 25 times. So the outcome for that is either heads or tails.
So, sir, 2 to the power of 25.
Okay, that's correct. No? The number of elements, no? Yung number of elements of our S here, if we consider this experiment, it would be equal to 2. No? For the first position, we have 2 possible outcome. It's either heads or tails. And then since we're going to toss it 25 times, so 2 to the power of 25. It's actually a large number. No? It's actually a large number. So if we are interested on the number of heads in this 25 tosses, then we might consider a smaller number, no, a smaller number of sample space. It's actually a sample space of a particular variable. And we call this variable as a random variable. A smaller number. So in other words, our sample space for our random variable x here, how many elements do we have? Kung ito ay yung sample space ng S natin, that is 2 to the 25. So if we consider x here as the number of heads in the 25 tosses, so how many possible number of, or ano yung mga possible number of tosses that we have in our outcome?
25.
Hindi ba kasali yung 0? Pwede naman sa outcome mo na walang
26
head.
guys, sir.
Diba? Pwede naman yung outcome mo na walang head if the number of heads. So we are just limiting ourselves on the 26 outcomes, or 26 possible values of our random variable x. Instead of dealing with a large number or the large number of elements in our sample space S. Okay, so we have here our definition now of our random variable. A random variable is a function from a sample space S into the set of real numbers. Say we have here our random variable. We denote it as capital letter X. It is a function from the sample space S, that's our sample space S, to the set of real numbers. Okay, set of real numbers. So in other words, the random variable is a way of expressing the outcome in our sample space as real number. Kasi kung meron kang outcome dito sa sample space S mo, say for example, we have here small w as an outcome in our sample space S, then we can express this outcome as a real number. So the image of this outcome w under your function x is actually a real number, element of R. I hope na naintindihan nyo yung mga notations dito. Okay, wala si Jan, no? How about Shera? Naintindihan lang ba yung mga notations dito?
Po, sir, okay lang po.
Okay, so X, no? The image of W here under X is an element of R. So in other words, we have here a new sample space. We call it as the sample space of our random variable X. And this sample space of our random variable X is actually a subset. No, it is a subset of the set of real number. And the notation for that, no? Yung range, ang tawag yan, the range of our random variable, since our random variable is a function, the range of X, this is what we call the sample space of the random variable X. It's being denoted by yan, itong symbol na yan. So this is the sample space of our random variable X. Okay, I'm not now referring to the sample space of our experiment. No, kasi yung sample space ng experiment natin, capital S. Ito ngayon, the sample space of our random variable X, we have that. So if we have this example, if you have this example, kung ito yung random variable X natin, ano yung ating range ng X or the sample space of X? Ito. Equal to what? Ano yung mga possible values ng X? Yun yung
0, 1, and 2.
Okay, that's correct, no? Tama, no? Hindi 1 and 2 hanggang 25. That's correct up here. So 0, 1 up to 25. So these are the possible values of our random variable X. When we say X equals to 0, kaya itong expression na to, when we have here, kung yan yung expression natin, X equals 0, this refers to an event. No, this refers to an event. This is actually the set of all small omega or small w in the sample space S such that X of W is equal to 0. So this is an outcome, no, it is an outcome in our sample space S such that the image of that outcome under X is equal to 0. So kung meron tayong outcome sa 25 na 25 tosses of a coin, lahat sila ang result niyan is 0, 0, 0. 0 lahat yung outcome. 0 lahat yung mga ibig sabihin head pala, tail pala lahat yung outcome in our on this W. So that means x of w here will be equal to 0 kasi walang head doon. Okay, so this is an event. This refers to an event. X equals 0. So I hope na naiintindihan nyo yan na kung meron tayong mga notation na ganito, say for example, capital letter X equals siya sa small x. So this capital letter X here refers to the random variable, while this small x here refers to the realized value, the realized value of our random variable x. Okay, so we have here other examples illustrating random variable, say the experiment of tossing 2 dice, and we take x here to be the sum of numbers. Okay, the sum of numbers. If we're going to toss 2 dice, if we're going to toss 2 dice, how many elements do we have in our sample space? Okay, that's correct, 36. So if we're going to 36 numbers lahat. 36 numbers lahat. Yung consider natin sa sample space S. But if we're going to consider a random variable x, which is the sum of numbers, ilan lahat yung sample space? 11. So meron tayong, mag-start tayo sa 2. Okay, 2, 3, and then 6 plus 6, 12. Kasali yung 12. So the total number, not 12, so 2, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 11 elements now, or 11 values, 11 values, possible values for our random variable x. Okay, that's correct here actually, 11 possible numbers of the random variable x, and then we can take our sample space of that random variable x. We have the script x there from 2 to 12. Okay, that's correct. Okay, so let's proceed now. So we have from our sample space S, we have now our new sample space, and that new sample space refers to the range of our random variable. Okay, so suppose now we have a sample space S. Ito yung sample space S natin, having these elements S sub 1 up to S sub n. Okay, that means our sample space is finite. And then we have this probability function P. Okay, then we define a random variable x with a range. Okay, that is our script x. It is the set of x sub I up to x sub m. And then we define a probability function P sub x on this new sample space script x on the following way. So we will observe that x equal to x sub I if and only if the outcome of the random experiment is in S sub j, element of S sub j, such that the x of S sub j will be equal to x sub I. Thus, we define this probability function P sub x of, okay, pinakita ko yan kanina, this refers to an event. So the P sub x of x equals to x sub I will be equal to, take note, we define this as our new probability function, a new function. Hindi pa natin yan na verify that it's a probability function. But we define a new function P sub x on the new sample space script x. And we define it to be equal to this P. Okay, this is a probability function. Ayan, sinabi naman dito kanina na probability function yan, which is the probability of this particular event. So we call this function P sub x as the induced probability, the induced probability function on the range of x. it is being defined in terms of the original function p. Makita naman dyan, defined in terms of the original function p. It's not difficult to show that you can verify that p sub x is indeed a probability function. It satisfies the three axioms, or the three Kolmogorov axioms. Pwede nyo yan siya ma-show. Ano nga yung tatlong axiom natin? A function p is a probability function. P is a function from the sigma algebra script B. Ano nga yung unang axiom? It says that the probability of A is non-negative for all A in the sigma algebra script B. Second axiom, you're going to show that the probability of the sample space S will be equal to 1. And then the third axiom, we have the probability, say we have a infinite collection of events that are a partition, partition of S, then the probability of the infinite union of the A sub i's here would be equal to the infinite summation of the probability of A sub I. So pwede nyo yan ma-check na itong P sub x here, this induced function is indeed a probability function. It satisfies the three Kolmogorov functions. We can see that in exercise 1.45. You try to answer this, baka, no? It might come out in your exam. Okay, so because of the equivalence in 1.4.1, we will simply write, we have here the probability of x equal to x sub I rather than this. So pwede na yan. Kaya makikita nyo yun sa mga book natin na instead of having this induced probability p sub x here, no, this induced probability p sub x here, we can just replace this simply by the ordinary, the original function p. Hence, indeed, the p sub x here is a probability function. Okay, any questions or clarifications on the definition of a random variable? By the way, we have a notation here, a note on notation. Random variables will always be denoted by uppercase letters of the English alphabet. Ang gagamitin natin, English alphabet na lang. And then the realized values of the variable or its range will be denoted by the corresponding lowercase letters. Thus, a random variable x can take the value small x. So, pwede natin ma-express ito, x here, pwede na yung ganun expression natin, equal to small x. Okay, let's have this example. Okay, consider again the experiment of tossing a fair coin 3 times. And after that, we define a random variable to be the number of heads obtained in the 3 tosses. So the complete enumeration of the value of x for each point in the sample space. So if we have, we're going to toss a fair coin 3 times, then the number of elements in our sample space would be 2 raised to 3, so we have 8. And these are the outcomes in our experiment. Nandito. So an outcome S could either be head, 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 tail, head, 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 and so on and so forth. If x is a random variable denoting the number of heads for our outcome, that is why we have here x of S. So if we take our S here to be HHH, the outcome HHH, then the number of heads would be equal to 3. And then for this outcome, HHT, so the number of heads is 2. So it would imply now that the range of our random variable x, this is our script x, would be equal to the set containing 0, 1, 2, 3. Because in this case, if the outcome is 0, 0, tail, 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 then the number of heads here would be equal to 0. Okay, now we can determine the induced probability function on our range of our random variable x. So for this small x here, it refers to the realized value of our random variable. It could either be 0, 1, 2, or 3. Then if we're going to look at our table above, then if we're going to compute for the induced probability such that x is equal, the probability of x equal to small x, if it is 0, so the probability will be equal to 1 over 8. Take note, we have a fair coin here. No? The outcome are equally likely. So we have 1 over 8 for that. And then if the outcome is equal to 1, we have only 1 over 1 head. So we have 3 over 8 for the probability. If you have 2 heads, 3 over 8, and then we have 3 heads, we have also 1 over 8. Okay, so we have here a specific computation of the induced probability. So it's the probability of this particular event, x equals 1. So ano yung mga outcomes in our sample space na isa lang yung head? So HTT, THT, and then TTH. So all in all, there are 3 outcomes out of the 8 outcomes. So we have 3 over 8. Okay, madali lang masyado yan. And then let's proceed now to the next example. Somehow it's a general example. The distribution of a random variable in which somehow the sample space is large. Marami masyado. Hindi na natin kailangan enumerate yung mga elements ng S. Gaya nitong first example natin, we enumerate all the elements of our sample spaces since there are only 8 outcomes. So ito yung nasa first row here. Pero kung hindi na natin may sulat o may enumerate lahat ng mga elements, we can still compute for the probability of a particular outcome. No? The probability of a particular value of our random variable. Say, let S here now be the 2 to the 50 strings of 50 zeros and ones. So yung 2 to the 50 is quite a large number. So, di na natin kailangan enumerate yung lahat. And then identify if x is the number of ones, then the range of this random variable x would be the set of numbers from 0, 1, to up to 50. So medyo mas maliit na lang yung sample space na kine-consider natin. Okay? So if we're going to take the probability, the probability that our random variable x is equal to 27, then we have this value for our probability. Okay, so yung number of strings na 50, 50 lahat, 50 strings of numbers, that would be 2 to the 50. That's the total number in our sample space. And then since we're picking only 27 ones out of this 50, so we have a combination of 50, say 50 string of objects, and then we take 27 of that, which is 1, over the total number of elements in our sample space. So for a specific value of the random variable x, which is 27, we can now compute for its probability. So in general, for any value of our random variable x, that is I, then we have this formula. Hence, we can now actually construct the probability distribution of our random variable. Okay? Any questions or clarifications? So we are actually on section 1.4 hanggang section 1.6 lang yata itong chapter 1. Then after chapter 1, discuss na tayo ng chapter 2. Any questions or clarifications? None so far? Okay.
So far, sir.
I'm going to continue my discussion tomorrow. I'm going to finish the whole chapter. Kasi kung mag-discuss ako ng 1.5 ngayon, patuloy kong yung remaining time na lang, meron tayong mga less than 15 minutes. Okay, so buti na lang na i-discuss ko ito bukas na lang. Yung section 1.5 and then section 1.6. Okay, so that's all for this afternoon. If you have no questions, muna tayo. Attendance na muna tayo before going to dismiss you. Ryan Cuenca? Naman to kanina si Ryan?
Sir, nawala daw yung internet.
Okay. Wala no? Jade Dalagan. Wala si Jade. Ryan Kier, present. Dina. Okay.
Present, sir.
Present. Mary Jean.
Present, sir.
Present. Marivic.
Present, sir.
Kim.
Present.
Noli. Last Noli.
Sir.
LJ.
Present, sir.
Shera.
Present, sir.
Christine. John Ray. Okay, so I hope that you're going to answer those important results na hindi ko na-solve kanina. No? Sinabi ko sa inyo, try yung mga exercises. Try to solve it at home. Maybe that will come out in the exam. Before we go, again, are there any questions or clarifications?
No, sir.
Okay, so I think wala na yata. So that's all for this afternoon. And, class dismiss.
So,
Okay, so I'm going to stop now the recording. Bye for now.